This video is an example problem of a charged particle through moving through an electric field. So I've got a particle to proton traveling between two plates, starting off at 4,000 meters per second. Plates are 5 millimeters apart. It's connected to a 1,000 volt battery. When I look at this, I can see the battery has a plus and minus side. Long line is being the positive, so that means the top plate's connected to the negative. It's negative side. Bottom plate's positive, and that's important for determining the electric field's direction. The question is, what is the proton's change in velocity after 10 microseconds? That's microseconds, 10 to the minus 6. So it's going to curve upwards because of the negative charge and the positive charge, negative plate and positive charge are going to pull it upwards. There's gravity acting on it, but it's not going to be as strong as the field in this case. In this case, horizontally, the velocity doesn't change because no forces are acting on it horizontally. Remember, that's what we're talking about, is velocities are our goal here. But vertically, there are two forces acting on it. There's going to be a weight and there's going to be an electrical field force acting on it. So vertically, the Vy will change after 10 microseconds. The initial velocity is going to look something like this, Vxo. It's traveling at 4,000 meters per second. After 10 microseconds, the horizontal velocity will not change, but vertically, it's going to move. It's going to accelerate. So vertically, it's going to have a different velocity. And the final velocity after 10 microseconds can be found from Pythagorean's theorem. V equals Vy squared plus Vx squared, square rooted. So that's going to give the velocity, the final velocity that I'm after. So it's going to be the final velocity minus the initial velocity. Now it's nice because I have a lot of these numbers already. The initial velocity is 4,000 meters per second, and part of the final answer is 4,000 meters per second. But I've got to find Vyo. So to find Vyo, I've got to find the acceleration. But to find the acceleration, I've got to use F equals ma and use the net force, which means I've got to use a free body diagram. So let's start there with the free body diagram. Okay, if I look at the givens that I have, I know the distance, the voltage, the charge, and the mass of the proton. And I also know the signs of the plates. That's going to help me with the direction of the magnetic field, electric field. I'm going to solve it like a projectile motion problem with two different accelerations, one vertical and one horizontal. So vertically, I know the beginning it's not moving up or down. I know the time is 10 nanoseconds, and the acceleration, if it were projectile motion, would be negative 9.8 meters per second squared. It's not, but just humor me for a few moments. Horizontally, it's 4,000 meters per second. The time is 10 nanoseconds, or actually 10 microseconds, and the velocity is still going to be 4,000 meters per second. Now, I said earlier, we'll treat it like it was projectile motion with negative 9.8, but it's not. So I'm not going to use that. I've got to find that acceleration vertically. So I'm going to start with a free body diagram. Here's the body, it's the proton. It's going to feel a force going down equal to the weight. And if I look at it, the proton's going to be attracted towards the top because the top plate is negative and the proton's positive. So that means that that's going to be the direction I'm pointing with my electric field, or the force due to the electric field. So I'm going to find the magnitude of the weight, W equals mg, using the mass of a proton. And that gives me the 1.6 times 10 to the negative 30 newtons going down. And then I'm going to use F equals QE to find the force due to the electric field, which means I don't have E. To find E, the electric field, I'm going to use V equals ED, or E is equal to V over D. So F is equal to QE. Then I'm going to substitute V over D for E. Putting in my numbers, I get 3.2 times 10 to the negative 17, which is a whole lot bigger than the weight. So when I find the difference in these two, the force going up minus the force going down, I get the net force to be basically the force of the electric field, or due to the electric field, of 3.2 times 10 to the negative 17 newtons. Alright, so that gives me a net force going up. Now I've got to find out what the net acceleration is. So the net acceleration is found from F equals ma, because I know the net force, I know the mass, so I can find the acceleration. So the acceleration is 3.2 times 10 to the negative 17 newtons divided by 9.11 times 10 to the negative 31. That should be kilograms, not meters per second squared, but kilograms. And that gives me an acceleration of 3.51 times 10 to the 13 meters per second squared. So that's the acceleration. Instead of 9.8, I'll use 3.5126 meters per second squared in that spot, not meters per second. Now I got to find the vertical velocity. So I know that vertically it's traveling at 0 to start with, times 10 nanoseconds, the acceleration, and I'm looking for V in the vertical column. So I'm going to use Vy equals Vy naught plus At, and when I plug in my numbers, so using acceleration of 3.51 times 10 to the 13, I get a final Vy of 3.51 times 10 to the 7 meters per second. But I'm not done. That's just Vy. Remember, for finding that velocity, you got to make a triangle. Vy and Vx. So 4,000 is Vx since it didn't change. Vy just calculated. Now use Pythagorean's theorem to find out the length of the hypotenuse that I've drawn. And that's going to be the final velocity. So the square root of 4,000 squared plus 3.51 times 10 to the 7 squared. Well, 4,000 is really small compared to the 3.51 times 10 to the 7. So it's not going to make much of a difference. I got to keep a lot of decimals before it actually shows up as making a difference. So in this case, the change in velocity is the final, which is the 3.5129 times 10 to the 7, and that's the hypotenuse. And it looks like it's just the vertical one I calculated, but that's because horizontally it wasn't a big number, minus 4,000 meters per second. And that gave me a change in velocity of 5.3125 times 10 to the 7 meters per second. So it's kind of a wrap up to all this. You're going to treat it like a projectile motion problem where the acceleration in the y direction is not 9.8, but you got to find it. And to find the acceleration, you're going to use a free body diagram and F equals ma to find the acceleration. Then you're going to use the vertical givens and kinematics to find the velocity, Vy. You're going to create a velocity triangle knowing that v squared equals vx squared plus vy squared. And the change in velocity is going to be the hypotenuse of that triangle minus the initial velocity.